The internet is often described as an invisible, omnipresent cloud. In reality, the backbone of our digital world is a physical, massive web of cables resting at the bottom of the ocean. All of those submarine cables and terrestrial cell towers are tethered to the ground. That physical infrastructure works for densely populated cities, but running fiber optic lines or building transmission towers requires stable land, immense capital, and continuous maintenance. Once you leave the urban centers, you hit massive geographic dead zones. The deep oceans, dense forests, and isolated disaster areas make up a huge percentage of the globe where ground-based coverage cannot reach. This geographic limit is a bottleneck for modern engineering. Emerging technologies like autonomous cargo ships navigating the open ocean or climate sensors monitoring remote glaciers cannot function safely on intermittent signals. They require a continuous, unbroken stream of data. We have laid out a viable ground to build on. To connect the entire planet, the architecture of the internet has to migrate into the sky. The first step up takes us into the troposphere. Here, high-altitude drones serve as the agile first layer of a non-terrestrial network. Unmanned aerial vehicles and high-altitude platforms are carrying transmission nodes, acting as highly mobile, deployable cell towers dispatched anywhere on a moment's notice. If a storm wipes out a city's ground infrastructure, drone swarms fly in and link together into an emergency network for first responders. Untethered, they reposition to optimize signal coverage where demand is heaviest, harvesting solar energy to stay aloft. But a drone swarm is a targeted local solution. To create a permanent, unified communication web across the Earth, the network requires a higher architectural tier. We move out into the exosphere. Here, thousands of satellites are currently being deployed to wrap the Earth in a synchronized orbital web. Geostationary satellites sit far away, causing latency. LEO satellites hover closer, cutting delays, but must travel 17,000 miles per hour to stay in orbit. To connect, dynamic routing continuously hands off data packets between satellites, keeping the user's connection steady. While this solves the global coverage gap, routing every single raw data packet from orbit back to servers on the ground for processing creates a bandwidth bottleneck. To prevent the system collapsing under its own data weight, engineers are pushing computational power out of Earth's data centers and directly into the sky. This transition is documented across current research, which now focuses heavily on integrating complex processing into non-terrestrial layers. In satellite edge computing, modern satellites don't just bounce signals, they use onboard AI processors to crunch numbers. When ground sensors transmit raw data, the satellite analyzes it in space, transmitting only the finalized, crucial calculations back to Earth. Processing data at this orbital edge reduces the amount of bandwidth required and helps eliminate the latency of sending uncompressed information back and forth through the atmosphere. By embedding logic and processing power into the hardware itself, we have transformed our orbital infrastructure into a globally distributed, floating data center. When you combine these distinct domains, you get the space-air-ground integrated network. Underground fiber optics, atmospheric drone swarms, and orbital satellites all merged into a single vertical architecture. Because the protocols are unified, a single data packet can now travel from a deep ocean monitor, beam up to a drone relay, hit an orbital processor, and route straight to a control room in a major city without a single interruption. On operational scale, this continuous link allows the precise, real-time coordination of autonomous shipping fleets, allowing them to navigate safely across remote oceans that were previously disconnected from the grid. This invisible infrastructure wrapping the globe functions as a synchronized computational brain. We have engineered our way past the geographic limits of the Earth's surface. By building a wireless planetary nervous system, physical disconnection is rapidly becoming a thing of the past.